Hi, we're Penn State Unmanned Aerial Systems, and we're excited to present to you our Flight Readiness Review to prove that we are ready for this year's AUVSI SUAS competition. Our team, composed of College of Engineering majors across aerospace engineering, computer science, computer engineering, electrical engineering, and mechanical engineering, has spent the last year preparing our UAS system. Hello, my name is Fabian Mendes, and I am an aerospace engineering student from the class of 2020. This has been my third year on our unmanned aerial systems team, and I have been involved with aeromechanical design and system engineering. This year I have been team president, and on the flight line I will be team captain and will be the main interface between the judges and our team.
Hello, my name is Zduniak. I'm a computer science major, class of 2020. I've been with Penn State UAS for 2 years, and my UAS experience pertains to communications networks and RF communications. My developmental responsibilities are electrical team lead, and I'll be responsible for communications networks on the flight line.
Hello, my name is Galkin. I'm a computer science student, class of 2019. I've been with UAS for 4 years, and my UAS experience is in systems programming for UAVs. On the development team, I've been leading the software division for the past 2 years, and on the flight line, I'll be responsible for manual classification.
Hi, my name is Ahmed. I'm a computer science major, class of 2019. I've been on UAS for 3 years now, responsible for interface design and implementation for ODLC. My developmental team responsibilities include designing the classification system, and on the flight line, I will be responsible for overseeing manual classification of targets.
Hi, my name is Ike Lagnice. I'm a mechanical engineering major, class of 2020. I've been on the UAS team for 2 years, and my UAS experience includes systems design and autopilot configuration. On the development team, I've been dealing with rover design and the payload release mechanism design, and on the flight line, I'll be manually classifying and overseeing the payload drop.
My name is Jubelirer, and I'm a computer engineering major, class of 2021. I've been at UAS for 2 years as the autopilot lead, and my day-to-day responsibilities are maintaining our path planning system as well as our autopilot system. On the flight line, I'll be in charge of obstacle avoidance and path planning.
My name is Brian Davis. I'm a mechanical engineering student with the class of 2021. I've been with the UAS club here at Penn State for the past 2 years. This year, I was the aircraft configuration lead, and some of my development team tasks include modifications to the helicopter platform, designing of the electronics enclosure, as well as testing procedures. This year at the competition, I will be the mission director.
Hi, I'm Carr. I'm a mechanical engineering student, class of 2021. This is my first year on the UAS team. I have experience with mechanical design and fabrication on UAVs. This year, on the developmental team, I designed mounting interfaces between system components and the airframe. On the flight line, I'll be the safety observer.
Hello, my name is Jonathan Reddy. I'm a computer science student, class of 2019. This is my 5th year on the team, and my experience regards to systems engineering for UAVs. On the development team, I developed this year's systems architecture. And on the flight line, I will be the ground control station operator.
Penn State's 2019 aircraft, the Phoenix, was built from a Mikado Logo 800. Modifications to the Mikado Logo 800 include enlarged landing gear, mounting plates for our avionics enclosure pod, and mounting points for our rover. The battery mounts were also changed in order to allow larger capacity batteries. In flight tests, we were able to reliably navigate at 30 knots, and our max speed tested was 62 knots. During a mixed flight of hover and cruise speed, we were able to achieve a flight time of 41 minutes. Sensors related to the imaging pipeline are placed inside the passive oscillation dampening system, which is separated mechanically from the rest of the aircraft. The pod weighs 890 grams full of sensors and has a resonant frequency of 13.2 Hz, well below the 28 Hz of the main rotor. Inside the pod are the dual camera system, the Wi-Fi data link, the Jetson TX2, and the Ethernet switch. Penn State UAS will attempt all tasks in the mission demonstration. We have a high degree of confidence in our autonomous flight, waypoint accuracy, and obstacle avoidance. For ODLC, we have medium confidence that our autonomous images will be classified correctly, while we have a high degree of confidence for actionable intelligence, geolocation, and characteristics. For airdrop, we have a high degree of confidence for accuracy and a medium degree confidence for driving to location. Penn State UAS has relied heavily on simulations to develop our system. Simulation data is then verified with unit tests and further verified with integration tests. During our flight tests, we have transitioned from manual to autonomous flight 13 times. To ensure ground resonance isn't added into our design, every time a mechanical change that may affect harmonics is added, a spin-up test is required. Before any real-world tests are done, all Autonomy's software is simulated in our high-fidelity simulation. The simulator we use is able to simulate sensor error as well as aircraft dynamics. In this video here, notice that there are two helicopters. One is the actual position and the other is the position that is estimated from the GPS. To determine waypoint accuracy, our mission telemetry logs are compared against the mission plan. Due to the battery failure and subsequent crash, we were not able to gather waypoint accuracy data in the field. We anticipate highly accurate waypoint accuracy because of our in-simulation tests and our sensor validation on the GPS. Due to the crash, we must also only rely on simulation data for obstacle avoidance statistics. Originally, we had some issues with the obstacles being hit. However, once we added a buffer of 15 feet to every obstacle, no obstacles were hit from that point on in the 1,000 obstacles that were tested in simulation. This year, due to the CSI MIPI cameras we utilized, we were able to provide a very lightweight, highly performant system that had a very wide field of view, allowing fewer passes to be able to get the same amount of imagery. Most of our best imagery test data was actually from the bus that drove by every 30 minutes in front of our lab. It would give us just enough time to try out a new system and figure out things like exposure time and focus, and the lettering was about the size of the smallest lettering that could be on a target, and the speed was about the speed that the aircraft was flying. Our ground resolution was high enough that for a 1 foot by 1 foot target, there were 1,748 pixels inside the target. Our low exposure time also minimized blur, meaning all images taken would be clear. Testing for object detection and localization involved testing on 89 images that had been taken with a multicopter carrying our payload and camera system. Images were captured at an altitude of 250 feet. Upon initial testing, we noticed that there were many more false positives than true positives, even though the true positives' characteristics were accurately classified. Because of this, the most prominent performance metric for detecting the pixel coordinates of targets was eliminating false positives. Objects are initially detected using scale invariant feature transformation, which highlights areas in an image where template shapes are geometrically similar to the features within the image. Then, each potential target is sent through a neural network trained on thousands of synthetically generated targets, which determines if the coordinates determined by SIFT are in fact that of a target. We ran the original test on the practice targets, but with our new implementation. This implementation was able to detect 88 of the 89 practice targets while producing only 3 false positives, giving us a very high confidence in our model's ability to eliminate false positives. In terms of the classification of the characteristics of the targets, we predict each of the characteristics using a robust convolutional neural network trained on 30,000 synthetically generated targets. We are very confident in the classification performance as each of the characteristics of the target can be classified with 87% accuracy or above. Our crash occurred before we had the chance to run localization tests on real-world data. Our IMU error is less than 1%, our GPS error is less than 4 feet. We expect localization to occur within 3 meters of the actual target. Our UGV system was developed around our winch drop system. The winch itself is contained in the UGV to reduce aircraft weight after the payload is dropped, and is speed controlled by a DC motor. The UGV utilizes a Pixhawk PX4 cube running ArduRover to navigate autonomously. The UGV is powered by 4 independent continuously rotating servos, which offer high enough speed and rotational control to navigate to the end position quickly and accurately. The UGV is also equipped with independent suspension for each wheel, which ensures further the rover will survive the ground drop and be able to navigate to its destination. Throughout our drop testing, we saw 85% survivability out of 20 drops. 3 complete failures occurred where continuous servos broke or structural components snapped. With a redesigned chassis and stronger servos, out of 5 full-speed drops, 1 servo failure occurred. However, the remaining servos were strong enough that the rover was still able to drive. In high winds, from a fixed point drop at 50 feet, we saw an average of 3 feet of drop variance from target location. Although our helicopter has a high-precision GPS, corrections being made while in windy conditions will randomly add to and dampen the oscillation effect of the falling payload, decreasing drop accuracy over the 100-foot drop to 10-foot accuracy. Our battery failure and subsequent crash occurred during developmental testing, and no full mission tests were ever conducted. We would score ourselves a 0 because they were not conducted. Though if the mission tests were conducted, we have high confidence that we would score well, close to 90%. The rest of this video will be a beautiful flight of our helicopter.
Yep.
Kerry, you comfortable with that? What's that? I'm good. Got over 200 feet away there. Feet away in 3 different directions. Does that count? Can I add it up? Yeah, can we add those up? You're going quick. That's 50 feet per second. That's 65 right there.